Hello everyone. I hope all of you are doing well. This is Shivam Aggarwal. Welcome to all of you to my YouTube channel Materials Physica. Today we will solve problems related to the crystal structure of materials. Now let us start to solve the problems. First problem. Calculate the packing fraction and the density of sodium chloride given that the radius of sodium ion is 0.98 angstrom, radius of chloride ion is 1.81 angstrom, radius of sodium ion. We will show this. And the radius of chloride ion, this will RCl negative. And the atomic mass of sodium is 22.99 atomic mass unit, and the atomic mass of the chlorine is 35.45 atomic mass unit. Now, let us calculate the packing fraction and the density of sodium chloride. Now, the formula for the packing fraction is equal to the volume occupied by the sodium and chloride ions in unit cell, and it is divided by the volume of the whole unit cell. So packing fraction is equal to volume of ions in unit cell over volume of unit cell. Here we have the radius of the sodium ions and the radius of chloride ion. So we can easily calculate the volume of the ions in the unit cell. But for the volume of the unit cell, we have to evaluate the value of the lattice parameter, because the volume of unit cell for a cubic crystal would be a cube. So volume of ions in the unit cell is equal to number of atoms of sodium ion in unit cell. We know sodium chloride is a FCC structure. So for FCC, the number of atoms per unit cell is 4. So 4 into volume of sodium ion, it would be because would be like a sphere. So the volume of sodium ion 4/3 pi r cube. And in similar way for chlorine ion, it should be 4/3 pi r chlorine over volume of unit cell, which should be equal to a cube, where a is this side and the 4 cubic, this is also a, and this is also a. So it is like a cubic cube. So the volume of cube is side cube. So now we have value of R, Na, RCl, but we have no value of a cube, a. So for value of a, we can see in this figure this is the chlorine ion, this is sodium ion, and this is again chlorine ion. So the distance between the center of adjacent chlorine ion is a, the lattice parameter, and this is the radius of chlorine ion from here to here, and this is the diameter of the sodium ion. It means 2Na, 2RNA, and this is the radius of chlorine ion. So it is the RCl. So A is equal to 2 times of radius of Na plus ion plus 2 times of radius of chlorine ion. So value of A is equal to 2 into radius of chlorine ion is radium sodium ion is 0.98 and radius of chlorine ion is 1.81. 0.98 plus 1.81. When we solve it, we will get A is equal to 5.58 angstrom. So now put the values of RNA, RCl and the value of A in this formula. We will get packing fraction is equal to we will get common 4/3 pi value of RCl RNA 0.98 cube plus 1.8 over cube of lattice parameter, that is 5.58. Now when we will solve this, we will get 0.663, or we can say 66.3%. This is our packing fraction. Now the second part of this question is the density of this crystal. For density, we know the formula for the density is mass of the unit cell over volume of the unit cell. Mass of unit cell over volume of unit cell. Here we know the atomic mass of the sodium ion and the atomic mass of chlorine ion. So in each unit cell we have 4 sodium ion and 4 chlorine ion. So the mass of the unit cell 4 into mass of sodium ion, and the mass of the sodium ion atomic mass in atomic mass unit is given 22.99. And atomic mass of chlorine is 35.45. These values are in atomic mass unit. So we have to change these values in kg or gram. So we know 1 AMU is equal to 1.66 into 10 to the power minus 27 kg. So put this value to convert atomic mass unit into kilogram. Now volume of this unit cell is A cube and the A is 5.58 angstrom. So our cube. And to convert this in meter, we will also multiply it with 10 power minus 10. So to get the density in kg per meter cube. So when we solve this, we will get the value of the density is 2234 kg per meter cube, or we can take this as 2.23 gram per centimeter cube. So now the packing fraction for this sodium chloride is the 66.3%, and the density of sodium chloride is 2.23 gram per centimeter cube. Now move on to the next question. Draw 101 and 11 planes in a cubic cell. Determine the Miller indices of the directions which are common to both of the planes. So here the two part of this question: draw 101 and 11 plane in a cubic cell, and the second part is the determine the Miller indices of the direction which are common to the both of the plane. Let us draw the 101 and the 11 plane in the cubic cell. For draw the planes, first of all we have to calculate the intercepts of these planes on the x, y, and z axis of the crystal. So for that, intercepts of plane 101 with axis. It should be the reciprocal of this. So 1 over 1, 1 over 0, and 1 over 1. This is for x axis, this is for y, and this is for z. So it is infinite. It means this plane is parallel to the y axis, and 1 over 1 is the 1. So it intersect. So it intersect at A on the x-axis. It is a parallel to the y-axis, and it intersect at B at z-axis. So it intersect at C at z-axis. So let us do this. This is our x, this is our y, and this is our z. For cubic structure, there is the cubic structure, and this is A, this is B, and this is C. For this plane 101, we can see it intersect x-axis at 1. It means at A. It is a parallel to the y-axis, so it does not intersect this, and it intersect z-axis at C. So it is a parallel to the y plane, sorry, y-axis. So intersect is a parallel to, so we can easily it will lie sorry, in such a way. It intersect x-axis at A, it intersect z-axis at C, and is a parallel to y. So this plane is our 101 plane. Now for the next plane is the 111. For that, intercept intercept of plane 111 at xyz axis with axis. So the reciprocal of and 1/1. Now it is 1, 1 and 1. It means this plane cut the x, y and z axis at the A, B and C. So now let us draw this plane. We can draw this plane. Oh, so okay. We will draw the next. So this is our x, this is our y, and this is our z, and this is our unit cell. This cut at A, this cut at B, and this is the lattice parameter C. So this is the unit cell of the cubic structure. Now the plane. It cut A, B, C at it cut X, Y, Z at A, B, and C. So it cut here, and it cut here. When we join, we will get this is the 111 plane. Now, the second part of this question is determine the Miller indices of the direction which are common to the both of the planes. So, for that, we have to know that the a law which is called V-zone law. What is the V-zone law? V-zone law state that if a lattice direction with Miller indices UVW is contained in a lattice plane with Miller indices H, K and L. Then it must satisfy this condition, which is HU plus KV plus LW is equal to 0. This is called the Wisdom law. It means that if UVW, Miller indices of the direction UVW is exist in a plane which have the Miller indices HKL, then it will satisfy the H into U plus K into V plus L into W should be equal to 0. This is called the Wisdom law. And our problem is the determine the Miller indices of the direction which are the common to the both of the plane. So in this question, we have to calculate the common direction indices which exist in the 101 plane and which also exist in the 111 plane. So now let us assume UVW is common direction of the both of the plane 101 and the 111. So for plane 101, it should satisfy U into 1 plus 0 into V and plus 1 into W is equal to 0. So U plus W is equal to 0, or we can say U is equal to minus W. Now same for 1 plane. U into 1 plus V into 1 plus W into 1 is equal to 0, or U plus V plus W is equal to 0. And we know U plus W is equal to 0. It implies V is equal to 0. So Miller indices of plane will be, Miller indices of direction will be U, V, W. And to convert this into simplest ratio, we have this is the minus W, this is 0, and this is W, or we will get 1 bar 0 and 1. In similar way, if we write W is equal to minus U, then we will get U 0 minus U, and to convert this in the simplest integer, we will get 1 0 1 bar. So this is the direction of plane which are common to both of the planes 101 and 111. Now the next question. Consider the crystal structure of the NaCl, which is the modeled as a set of the touching sphere. Each Na atom has the radius of R1 and each chlorine atom has the radius R2. The center of the sphere forms a simple cubic structure. The packing fraction of the system is. So we have to calculate the packing fraction when we have only the radius of the chlorine ion and the sodium ion. So this is the same as the first question which we have solved previously. So packing formula for the packing fraction is equal to volume of ions in unit cell over volume of unit cell. And the volume of the ion, because it is a FCC structure for the sodium chloride, so it would be the 4 into volume of sodium ion, and it is the have the radius r1, so it would be 4 over 3 pi r1 cube, plus it has a 4 chlorine ion, so the volume of the chlorine ion 4 over 3 pi r2 cube over volume of the unit cell. In the first question, we have seen the lattice parameter would be equal to the 2 radius of sodium ion plus 2 radius of chlorine ion, and we can take common 2, it will become 2 RNA plus 2 RCl. So here we have R1 at the place of RNA, and we have R2 at the place of radius of chlorine. So it is value of A, and it means lattice parameter. So it would be the 16 over 3 pi and R1 cube plus R2 cube over, it will become common 8, and it would become R1 plus R2 cube. 8 2s are 16, and it will become 2 over 3 pi R1 cube plus R2 cube over R1 plus R2 cube. This is the answer for this question. Now, question, find the ratio of the atomic densities in BCC and the FCC solid. Assume the lattice constant in BCC is the 2.0 angstrom, and in FCC it is a 4.0 angstrom. So we have to calculate the ratio of the atomic densities. The formula for the atomic density, rho n is equal to number of atom unit cell over volume of unit cell. So we know number of atoms in BCC structure is n. BCC structure is the 2, and number of atom in FCC structure is 4. 8 atoms at the corner, and 3 atoms and 6 atoms at the faces of the faces of the cube. Now we have to calculate the ratio of the atomic densities. So rho n BCC over rho n FCC would be equal to the number of atoms at the BCC over volume of BCC structure, and it would be the ABCC power cube, and rho n FCC, the number of atom of FCC unit cell, and the volume of FCC structure, FCC unit cell. So, and BCC is 2, and lattice parameter is 2 for the FCC, and it's a 4 for 2 for BCC and 4 for FCC, and n for FCC is the 4, and when we solve it we will get the answer 4. So the ratio of the atomic density in BCC and the FCC solids is 4. Now, so BCC structure. So for this, BCC structure is more dense than FCC solid for this question. Now the next, a certain orthorhombic crystal has the axial units A ratio B ratio C of 0.424 ratio 1 ratio 0.367. It has A ratio B ratio C equivalent to 0.424 ratio 1 ratio 0.367. Now the ratio of intercepts is 0.212 ratio 1 ratio 0.183. Now this is XYZ axis of the crystal. Then the plane cut at these points. So let us assume this distance is MA, and this distance is at the which is cut at the y-axis is the NB, and this is let at this cut is PC. Now, so the MA ratio NB ratio PC is given according to our question is 0.212 ratio 1 ratio 0.183. But when we calculate the Miller indices of the any plane, we want the ratio ratio of the intercept in terms of the multiple of the lattice parameter. So we want M ratio N ratio P. So A ratio B ratio C is given as the 0.424 ratio 1 ratio 0.367. So ratio M ratio N ratio P ratio P be equal to 0.212 over 0.424 ratio 1 over 1 ratio 0.183 over 0.367, or when we simplify we will get 1 over 2 ratio 1 ratio 1 over 2. So M ratio N ratio P is given as 1 over 2 ratio 1 ratio 1 over 2. It means this plane cut x-axis at 1 over 2A, it cut y-axis at B, and it cut z-axis at half C. So we want this ratio for the Miller indices. Now calculate the Miller indices. Ratio of intercept in terms A, B, and C is 1 by 2, 1 by 2, so 1 by 2, 1 and 1 by 2. So after that, we have to take reciprocal of the intercepts. The reciprocal become 2, 1, 2. And after that, we have to change this into the minimum integers. So it is already in the form of the minimum integer. So after that, we have to change. We have to put these numbers in bracket. So it will become 2, 1, 2. And this is the Miller indices of the plane. Now, let us move on to the next question. In a unit cell of the simple cubic structure, find the angle between the normals to the pair of the planes whose Miller indices are 1, 2, 1 and 1, 1, 1. We have the formula for the angle between the normals to the pair of the planes, which have the Miller indices h1, k1, l1 and the h2, k2, l2 is given by theta is equal to cos inverse h1 h2 plus k1 into k2 plus l1 into l2 over under root h1 square plus k1 square plus l1 square under root h2 square plus k2 square plus l2 square. Now this is h1, this is k1, this is l1, this is h2, this is k2, this is l2. Now put the values of all of these, we will get 1 into 1 plus 2 into 1 plus 1 into 1 over under root 1 square plus 2 square plus 1 and 1 square plus 1 square plus 1 square. After solving this, we will get 2 root 2 over 3 and cos inverse 2 root 2 over 3 we will get 19.47 degree. This is the value of theta. Now move on to the next question. Now move on to the next question. The primitive translation vector of the two-dimensional lattice R A is equal to 2i plus j and b is equal to 2j. Determine the primitive translation vector of its reciprocals. So the primitive translation vector of the two-dimensional is given as a and b. Now let us assume there is a third vector which is perpendicular to both of this vector is k. So c is equal to k cap. And now we know now we know that the primitive translation vector of its reciprocal is given as a dash vector is equal to 2 pi b cross c over volume of the primitive cell, which is given as a vector dot b cross c. And in similar way, b dash will be given as 2 pi c cross a over volume of the cell a dot b cross c, and we have taken the mode of this. Okay. Now 2 pi b cross c. First we can calculate a can calculate the volume of the unit cell is a dot b cross c. A is 2i plus j and the dot, and the b vector is 2j cross, and the k is c is the k vector. So 2j cross k, we know j cross k is I, so it will become 2i plus j dot 2i. When we will dot product I dot I is 1 and I dot j is 0. So it will become 2 to the 4 into 1. So volume of this unit cell is 4. And we can also calculate B cross C and C cross A. B cross C is value of B is 2j, cross is a C is a K, and it will become J cross K is I. So it is 2I. Now the C cross A, C is a K cap cross 2I plus J. We know K cross I is J, so it is 2J, and the K cross I is minus, oh sorry, 2 cross J, oh sorry, K cross J is minus I, so it is minus I. So we will get the value of the A dot B cross C, B cross C, and C cross A. Where now we will put this value in this formulas to get value of A dash and B dash. Value of A dash vector is 2 pi, and value of B cross C we will get 2I cap over, and the volume of cell is a 4, so A cap become, so sorry, A dash vector become 2 pi I, and B dash vector is the 2 pi C cross A over volume, so it will become 2 pi, and C cross A we will get 2j minus I and over 4. So it is become, sorry, it is become minus pi by 2 I plus pi j. So we will get the A dash vector and the B dash vector. So this is the translation vector, primitive translation vector of the reciprocal lattice for this 2D. We can also visualize that 2I plus j. So this point is, so this is our A vector, and the B vector is equal to 2j, and there this is our B vector. When we draw this lattice 2D lattice by this translation vector A and B, we will get A plus 2j, we will get the point here, and after that 2j we will get here, and when we apply the 2I plus j here, we will get the point here, and after apply 2j we will get here. So in this similar way we will get the other lattice point, like here also, here, here, and here, here, this one, and this one, this one, this one, and this one. Okay. Sorry, this is not this one and this one. Thank you so much for listening me. If you have any other question and other any feedback, you can comment in the comment section. Thank you so much for listening me. Bye bye.